Hey y'all, hopefully just recently I worked on this project with a friend to create L systems that are drawn in real time using a combination of Python and Scheme. Basically what this program does is it takes in a few parameters that you need in order to run create an L system. Outputs that into a string that can be parsed and drawn in real time. So, to start things off, it's just a few parameters, and it'll be able to draw these interesting shapes. So let's go with a classic. Let's go with an approximation of a Sierpinski triangle. So this is our starting string. This is rule 1. This is rule 2. I'm going to do 6 iterations. 20, no special case. And what we see here, you see our little turtle graphics engine going ahead and drawing Sierpinski triangle just out of thin air. So how does this work? So what an L system is, it's a recursively generated string of instructions that are then carried out by this turtle here and that are drawn. So what I just showed you is that first it needs a starting string. So we saw 0, minus 1, minus 1. And then it needs rules for each of those variables 0 and 1 to go to. So for every iteration, every 0 turns into 0 minus 1 plus 0 plus 1 minus 0. You can see it's done now. And every 1 goes into 1, 1. And what ends up happening is that first it creates, just one little triangle, and it creates another one, and then a bigger one, and then a bigger one, and then eventually the string can create a shape like this. So let's do the same shape again, just to reiterate this. We can do the same shape again. Punch in all this stuff. We're just gonna do 2 iterations. We're gonna see what that draws. So you see very little itty bitty version of it here, but just that 0 minus 1 minus 1 turns into 0 minus 1 plus 0 plus 1 minus 0 minus 1 1 minus 1 1, and then that allows you to get this shape. So what do those minus plus minuses mean? So L systems also operate under some constants. So plus and minus dictate rotation. So a minus will rotate the cursor counterclockwise by the given angle, in this case 120, and then right conversely rotates clockwise 120 degrees. So what ends up happening is you can get cool stuff like this. Just these little triangles here. So let's do some other ones. Let's show off a different constant. Oh yes, and variables in this context, each time the parser encounters a 0 or a 1, it just draws forward by our pen length, which happens to be 20 pixels. So let's do a little more complicated one. Do one of these. This one only uses one variable, but it uses a new tool, which is the stack. Put this in here. This one's quite a long one. We can't do a lot of iterations without crashing here, but let's say we'll do 4. All right. 35 degree angle. So let's Still no special case. So this uh, this this particular L system incorporates a stack, which is very simply just saving the rotation and position, and then popping that position whenever the parser encounters a closed bracket. So it'll basically every time it'll go forward, save its position, rotate, go forward twice, go back, rotate, go forward twice, go back, go forward, save its position, rotate, go forward, go back, rotate, go forward, go back, go forward, over and over and over and over again. And even with that simple pattern, and with the use of the stack, you're able to get these very cool kind of branch-like fractal patterns. This is a type of fractal called a Barnsley fern, basically a fractal that looks like a plant. This is one of the longer ones, so I'm not going to let this play out entirely, but basically it'll finish this canopy here, and then it'll draw two more off to the side. So this one takes quite a bit, but it's very mesmerizing to watch happen. Very cool. So let's get to these. I showed it off a little bit here, but there's some special cases that go along with these as well. We'll just stop this here. We'll start with the first one, the binary tree. So this particular L system actually does not incorporate plus or minus. It does not rotate in that conventional way. But what it does do, let's do 7. And then this would be a tree. The way it rotates, oh geez, I think it's going to draw off the screen pretty quick here. But instead of using plus and minus to dictate rotation, now the tree uses the stack to dictate when it rotates. So whenever you put something onto the stack, rotate counterclockwise 45 degrees. And whenever you pop something off the stack, you go back to your position and you rotate to the right 45 degrees. So then you get a cool little pattern like this. Let's talk about our other special case. So this one's a little silly. This is the plant exception. Explain why it's called that in a second. It's not like an official term or anything, but essentially called it the plant because it's used in this one particular plant-like fractal. We are in 25 degrees. Oh wait, oops. Don't want to iterate 25 times. It'll brick the program. So every time the parser encounters a 0, it does not draw forward. It's just kind of a hold. So what that allows the program to do is to rotate and get some steeper angles off of rotations if it so desires. You see there, it's kind of rewriting over itself a little bit. Some of these plant fractals have a tendency to do that. Pretty interesting. But you see it's trucking along here. You're able to get very slight angles, as you can see right here on this little branch, or you can get some more steeper stuff. As you can see here, it's pretty. This one's pretty sharp. This one's pretty sharp down here. So you're able to get this very organic looking little stick plant. So very cool. Those are just the two special things, a couple exceptions we put in here. Unfortunately, there are a few limitations with this. You can only have two variables. We didn't have space to do more than two. And you can only do so many iterations, unfortunately, since Python's recursive depth is very low. We even juiced it up a little bit for this project, but even still, it's a bit limiting. So you can't go more than just a few iterations deep before Python runs out of memory. So that's too bad. For example, this one, I think 5, which is what I did, is the maximum it can take without shattering, unfortunately. But there's still plenty of shapes you can make despite these limitations. So I hope you can poke around with this and make some cool shapes. I have all the files you'll need into a GitHub in the description. So let's talk a little bit about how this works. Now, what's going on with this? It's cutting me off a little bit down here. There's still code, but I think you can see it. Alright, we'll just have to zoom out a little bit. Alright, so essentially the way this works is takes in inputs, a couple set of inputs from the user, and then we run a scheme program that allows us to generate this string recursively. So you can see here, our little algorithm here. Basically what this does is it takes in our two rules, replaces them recursively a bunch of times, iterates through however many iterations there are, and then confines that into one list altogether and then returns it. This was put together by a colleague, I guess you could say, friend of mine. Pretty cool stuff. Found a pretty esoteric Python scheme, Python library that allows us to run scheme code in Python. I'm surprised such a thing even existed, but we're glad it does. Then takes the output and puts it into our little string here, which Python can then read. We take a couple more inputs, like the angle and the special case, and then we go ahead and run it. Here's our parser here. This little method here basically allows us to input all of the rules and replace certain digits with constants. This allows us to make the string. There's still some space here. I suppose, unfortunately, limitations of our own knowledge, we could only manage to do numbers in this equation in our scheme script here, but there is a little bit more room for more variables, but I mean, you can hack it together if you'd like. All you have to do is, well, you can figure it out. Limitations of time and whatnot. But this basically puts everything into the scheme code, which then runs and then splits and puts it into a string that Python can parse. So here's our parser here. We use something called turtle graphics, which is essentially you have a little turtle or cursor that can be rotated or told to draw forward or go to specific coordinates. You can see here, basically every time there's a variable pushes forward, and then rotation constants, turns left and right, and the stack here we just used a Python list. And then here is the binary tree version that only uses the stack. So that's basically the meat of the program. Pretty cool what you're able to do with just a few tools, a few principles of mathematics. You're able to make some pretty cool shapes. So I guess I'll do one more to round us off here. Let's do the dragon curve. This one's a pretty famous fractal here. This one, since it's so simple, it can take quite a few iterations. Double digits, incredible. Oops. There. Yeah, also, there's no way to adjust the screen space depending on the fractal. So if you end up drawing something off the screen, sorry, you can change the canvas size manually if you so choose. I think we'll be able to get everything on the screen here anyway. We'll see. It's getting kind of close. Maybe. Oh, it's looping back around. All right, I think we're in the clear. These are pretty cool. Oh. There it goes. Too bad. If you're curious, the world coordinates start at 0, 0 by default. That's right in the middle of the screen. It's great sometimes, but also if you have bigger shapes like the Sierpinski triangle or the binary tree, you end up having your space. So, but sometimes you do get kind of centralized stuff like this, and it kind of goes off into oblivion. There's the dragon curve. All right, what the hell? One more. Let's do the Cope curve with 90-degree angles. Then we'll call it this one may also. It's just 0. This one may also draw off the screen. Let's do 5. Nice. All right. Let's see. There you go. Pretty cool. All right. So there is my little project that I did. Hope it's going to go way off the screen. But hope you enjoyed it. Again, this is I have a GitHub link in the description. If you want to poke around with this yourself, see what kind of shenanigans you can make. But I hope you enjoyed looking at some cool shapes getting drawn. Pretty fun, rewarding experience to see this actually work. The math does indeed work. Very fun to see happen. So just the tail end of it cut off there. It's too bad. All right, but that's all I got. Thank you very much for watching. Hope you enjoyed it. Bye-bye.